Welcome to our video on complexity analysis for computing the square of a graph. If you're interested in graph theory or computer science, this topic is definitely worth exploring. In this video, we'll delve into the concept of squaring a graph and how it relates to computational complexity. Computing the square of a graph is an important operation in various fields, such as network analysis, data mining, and computer vision. However, as graphs grow larger and more complex, computing their squares can become computationally expensive. That's where complexity analysis comes in, helping us understand the time and space requirements for this operation. In this video, we'll break down the concept of graph squaring, explain its significance, and analyze its computational complexity. By the end of this discussion, you'll have a solid grasp of the key concepts and be able to apply them to your own work or studies. So let's start with the basics. What is a graph square? Simply put, it's a new graph where each vertex represents an edge from the original graph. Two vertices in the squared graph are connected if their corresponding edges share a common endpoint in the original graph. This operation has various applications, such as clustering and community detection. Now, let's dive into the complexity analysis of computing a graph square. There are two main approaches, iterative and recursive. The iterative method uses a simple loop to iterate over all edges in the graph, while the recursive approach employs a divide and conquer strategy. The time complexity for both methods depends on the size of the input graph. For the iterative approach, it's OE, where E represents the number of edges. This is because we only need to visit each edge once. On the other hand, the recursive method has a time complexity of OVE, where V is the number of vertices. This is due to the additional overhead of function calls and stack operations. However, there's a catch. The squared graph can have up to V2 edges in the worst case, leading to an explosion in memory usage for large inputs. To mitigate this issue, we can employ more efficient data structures or use approximation. Another crucial aspect is the space complexity of both approaches. The iterative method typically requires extra space for storing temporary results, while the recursive approach needs OVE due to the function call stack. Again, this highlights the importance of optimizing memory usage when working with large graphs. To recap, we've covered the concept of graph squaring and its significance. Two main approaches for computing a graph square: iterative and recursive. Time complexity analysis for both methods, OE vs OVE. Space complexity, considerations for large inputs. That's it for today's video on complexity analysis for computing the square of a graph. We hope you now have a better understanding of this important topic and its implications in computer science. If you have any questions or need further clarification, please don't hesitate to ask in the comments below. Your feedback is valuable to us. Also, if you found this video informative, be sure to like it and subscribe for more content on graph theory and computer science topics. In our next video, we'll explore another fascinating topic in the world of graphs. Stay tuned!